Good afternoon. Welcome to everybody who decided to join Sano for this seminar. And it is a kind of special seminar because today we have, as speakers, we have four our STEM ladies. So Sano is organizing a kind of scholarship, and it is a kind of, let's say, competition, and a number of girls obtained this scholarship. And in March we had the first part of these presentations. Today we'll have a second part of this talk, and there will be 4 talks. After each talk, it will be possible to comment and also to ask questions to our ladies. So the first will be Katarzyna Libera. Kasiu, screen is yours, floor is yours.
Thank you very much. Hi everyone, my name is Katarzyna Libera and I work in the team of computational neuroscience. My supervisors are Jamal Koba and Jan Gasiński. To give you a quick introduction, I am a second-year bachelor student at the Faculty of Physics, University of Warsaw. And as you can see, I study physics, neuroscience, and a bit of computer science. And I chose this combination because I feel like it can give me a good background to problem solve in neuroscience and grasp also advanced technological concepts. And I also simply, enjoy electromagnetism and mechanics, which is really fortunate because my physics background was particularly helpful for me in the project that I'm working in Sano with MRI technology, which I will explain in a bit. First of all, my interests. I am currently most interested in imaging techniques, especially MRI, which I work with in Sano. But during my project, I've also grown more and more interested in vision itself, both when it comes to ocular abnormalities and as well as vision restoration technology, which is more of an outside research interest. And also, when it comes to my non-scientific interests, I like to spend my free time actively. I play volleyball, as you can see, and I also enjoy cycling, running, team sports, as well as I very much enjoy going to the theater or the opera. My main project at Sano is focused on Jamal Koba's research project, which is linking eye movements and brain function to monitor stroke-induced alterations with fMRI. And my objectives include the analysis and processing of diffusion MRI and anatomical MRI data. And my main focus is on developing a robust pipeline for tractography generation from both stroke patients and healthy controls. And you can see an example image of what diffusion tractography looks like, even 2 images. I am also working on the next logical step, which is connectome metric generation from the acquired data. And you can also see one of these here as an example. And one of the main goals here is to get, as I said, a standardized and optimal connectome generation pipeline for the whole data set, and also get an additional marker for the eye movement abnormalities. And additionally, I'm working with another student on generating a map of the white matter tracts that were affected by stroke using lesion masks. And in this April, I also gave a poster presentation and a flash talk about my work in the project, and it consisted of 2 stages of comparative analysis. One taking only the acute stage of the stroke cohort, and also another one focusing on the longitudinal effects. So basically, we tested ocular features and compared them to the structural markers that covered both large-scale characteristics of the brain as well as microstructural changes. And Those were derived from the diffusion MRI data from my pipeline. And we also tested associations of the changes of those features over time and included it in the study. And in short, to just sum it up, we found significant associations of in the acute stage analysis and had some suggestive results in the longitudinal one, but the fully processed longitudinal data set is still under construction. So we are currently working on getting all the lesion masks for the follow-up sessions, and there is still much to anticipate here. Yes, and my plans for the future. So well, I definitely want to further progress and get more experience in computational neuroscience. And I am really happy that MRI imaging is the intersection of neuroscience and physics, because this combination helps me get the full image of the scientific problems. And as I mentioned previously, I'm especially interested in eyes and vision in general. So I would naturally like to continue down this current path and maybe also explore topics adjacent to eye movement abnormalities, such as perception, vision, restoration in blindness. And I also plan on pursuing a master's degree in computational neuroscience. And yes, so thank you very much. That's it from me, and I hope you enjoyed my little get to know me, and I want to thank you very much for listening. Thank you.
Kasiu, thank you very much for your presentation. Well, maybe Jamal, would you like to add something to this talk?
Sure. I mean, what I can add is Kasia helped us a lot with the processing of diffusion data. She spent her whole summer here suffering by learning diffusion analysis. And I really think she did a great job managing, creating a pipeline to process the whole data set. And now, yeah, thanks for her efforts, we can use the diffusion data from the data set we have. And yes, I think we will keep collaborating throughout the summer and maybe next year, depending on her interests.
Well, do you think that this collaboration will result in the publication, the paper?
Well, this is already a part of the huge data set we are using. We had the fMRI data and eye movement markers from fMRI and clinical data. And I'm integrating the structural data that we derived thanks to her efforts to the data set, and we are using them in the calculations.
So I have a question to Kasia. How you can, is it easy to combine this internship with your study?
Do you mean the university?
Yes.
Yes. So I was working part-time during my scholarship, and now I'm back to like working just as a voluntary on a voluntary basis. But yeah, I'm doing my bachelor's currently. So
So it, as I understand, it will be in the year from now, yes. So your bachelor degree you should obtain the bachelor degree in something like a year from now, yes?
Yes.
Yeah, so maybe we can write the thesis about the work she does here.
Well, but it will require collaboration with somebody, supervisor from the university, of course. Yes?
Yeah, sure, definitely.
Thank you, Kasia, very much. And we'll move to the next person who will be this next person.
Me, Julia Rybska. So, hello everyone, I'm Julia Rybska, and today I want to share with you a little bit about myself, and what I'm focusing on in here is summarized in this title, which is Deep Learning for Survival Analysis in Glioblastoma, based on white matter density maps. And my supervisor here is Joan Falco-Roger. Somewhere? Oh, there. Okay. So to start, I wanted to mention how I got here, which wasn't that straightforward. So I started in automatics and robotics, which was rather technical. I didn't really have any biology or medicine related courses, but I had always been interested in how the brain works, and that led me to ask around, and I ended up writing a thesis in emotion recognition from EEG signals, which was my first encounter with using machine learning for brain data, and I realized that that's something that I'm really interested in. So I started looking for opportunities, and I went to Winter School of Ethics in Neuroscience and AI, where I met people from the field, which further inspired me to pursue that. And along the way, I applied for my master's degree in computer science with the specialization in machine learning and AI to gain the technical knowledge that I can, and also practical, that I can later apply to hopefully medical applications. And from the beginning, I knew that I wanted to write a thesis related to neuroscience. And after some months, I managed to become part of this project. And first, a little background on the problem. So glioblastomas are the most aggressive brain tumors with 12 to 15 months of mean survival with standard treatment already. So there's a need for improved survival prediction and also disease understanding. And recent evidence suggests that it's not a separate entity within the brain, but rather glioblastoma cells establish functional links with neurons, which forms the basis for treating them as part of the whole network and looking at white matter more closely. So our goal is to map the glioblastoma circuit and its relationship with prognosis using non-invasive methods. And on the left, you can see the data modality that is based on all the things I mentioned in the previous slide. So these are 3D volumes of tract densities, which can be interpreted as subsets of white matter tracts that intersect tumor masks of each patient. And since this data is highly dimensional, around over 1 million voxels, this justifies the use of deep learning that has the ability to learn nonlinear patterns and compress information to possibly extract features from this high dimensional data. And also you can experiment with various architectures, possibly allowing you to solve the problems that you want. Mm-hmm. And the questions I asked myself and tried to answer by using these models, you can see on the right. So can the lower dimensional space be interpreted in any way? Do the found latent representations relate to survival? And can we improve survival prediction? So here I'm just showing that initially I implemented a simple autoencoder architecture. So it's a 3D convolutional autoencoder where as input we take the whole 3D volumes, and I have the autoencoder has convolutional layers that are followed by a fully connected layer, and the size of this latent space is customizable. And the interesting part here is that we can analyze it and use it as input to Cox survival models, which lets us analyze the input on survival, which I'll describe in a bit more detail in a second. So into some of the results that I have. On the left, you can see the loss curves. So you can see that the network does learn something. And on the right, you can see all of the volumes of patients mapped onto the 2D space after the compression of the trained encoder part of the autoencoder. In this slide, you can see the reconstructions. So it allows to think that possibly the latent space is meaningful since the reconstructions look reasonable. And as I mentioned, we want to interpret these latent representations in terms of survival. And for that, the Cox survival model is useful. So it models the hazard, which is the risk of a patient dying at a given moment, given that they survived until that point in time. And it depends on a set of covariates. And as you can see here, they can be different covariates, such as clinical ones like age or sex or different clinical covariates. Or we can also treat these latent representations as a covariate and feed that to the Cox model. And the output we get is a hazard per patient and also p-values for all of the covariates that were tested, which indicate whether they have influence on survival or not. And the results I obtained for that for a 4-dimensional latent space showed that one of the elements of this latent vector had a p-value close to being significant. And later I fit the model using 2 clinical covariates of age and sex and this one element of the vector. And it had the p-value of 0.03, which is the basis to believe that there's more to explore here. And yes, it's preliminary evidence that there's potentially something worth there. And as to what my next steps are, the first question is whether maybe there's too much compression, so perhaps a bigger latent space will allow for markers that can help us analyze survival better, that influence survival. So I want to run a more complex analysis of different sizes of the latent space. For that, I want to make the code runnable in Cybernet because the training does take a while, so it will help. I want to experiment with more sophisticated architectures potentially and to try different loss functions. For example, adding a survival component to them to check whether then the network can show us something about related to survival. And of course, last but not least, we want to put focus on anatomical and clinical interpretability, which is always part of the pipeline, but perhaps using some deep learning explainability methods can also show us something interesting. And the last slide now is the lessons learned while working here. The first one is don't trust AI, especially when it's convincing. And of course, I think we all agree that it's a useful tool. But on the right, you can see reconstructions that I got when I implemented a loss function that was suggested. It was really convincing, but as you can see, it didn't work well. And the reconstructions I showed previously were better. Then I have this loop of read, think you get it, experiment, get lost, and then repeat, which I hear is what happens, and I have experienced that. And the last thing is that any conversation I have here in the office is really inspirational. So that's what I'm for sure thankful for. And as to my scientific future, I will present the findings from this research in FENS in Barcelona this year in July. And then I'm hoping to defend my master's thesis this year in September. And then I put 3 question marks because I'm not fully sure where this will take me further. But I am excited to see how this unfolds.
Thank you very much. Thank you very much for this talk. Well, let's follow the pattern which we applied in case of Kasia. Maybe Jean, could you add something?
I think she did a great job. Yeah, so her and Basha, which I suppose we'll talk now or later, are exploring how useful it is, this representation that we came up with in using white matter density instead of normal MRI. And we could ignore the process and just feed everything to an AI model that is powerful enough, but I am interested to see what this modality alone can give us. But yeah, the idea is been quite well explained, I think, unless there are specific questions to it. So,
well, this neural network was something standard, or it was just specially invented for this case? Or?
No, just like a simple autoencoder architecture. It's a 3D one, so it operates on whole 3D volumes, but no, for now I wouldn't call it a very sophisticated one, just a simple one to see, to get some initial insights.
I understand. So it could be somehow extended without well, I understand that the poster means that it is at least abstract of this research is published in the material for this conference, and your Master of Science thesis will be somehow related to it.
Yes. So this is yes, I'm not sure how to answer. So that is the topic of my master's thesis, but I think perhaps it's there are some differences in what kind of results are the most important in here and what kind of results are the most important at the university. So there needs to be some connection done there, I think. But yes, that is the plan.
So do you, as I understand, you expect to define this thesis this year, yes?
Yes, I hope so.
There are many different competitions for best master thesis, so please don't forget about this.
Okay.
Well, any other comments or questions? If not, thank you once again.
Thank you.
And we can move to, okay, as a first presentation, really presentation on the research done by Barbara Wojtarowicz. So Barbara.
Hello, so I'm Barbara Wojtarowicz. Hello everyone. And this is the topic of my master's thesis that I'm realizing here at Sano, investigating the impact of tract density indices from glioma components on patient survival prediction using machine learning. This topic, however, needs to be a little bit adjusted due to the research, how the research went. A little bit about my background. Excuse me, I need to move a window on my screen. I obtained Bachelor of Engineering degree in Computer Science at AGH University of Krakow with a thesis, Software Tools for Community Detection in Brain Networks using Quantum Solvers, which was my first opportunity to work with human connectome that I am very grateful for. And now I am doing my master's degree in computer science at the same university with my thesis that thesis topic that I just showed you. So it's very convenient that.
Please tell us who is your supervisor.
Yeah, I was hoping to. So it's very convenient that Julia started with her presentation because we're in the same team, computational neuroscience. My supervisor is Jean Alkorożet and Dr. Jan Argasiński. And yes, so this is my team. So as Julia mentioned, glioblastoma is a devastating disease with overall median survival approximately 12 to 15 months. And current lines of research in neuro-oncology focus on the connectomic-based survival prediction approach, as glioma cancer cells tends to infiltrate the surrounding white matter and pass along white matter tracts. So that's like foundation why we are doing what we are doing. Here in the picture, we can see with the red arrow, the cancer cells propagation, like the cancer cells spreading along the axon fibers. And I'm sure we are all aware of the already existing solutions that the computational neuroscience team developed. So the lesion tract density index combined with clinical features to get an enriched tract density informed feature set that is later being fed to survival prediction models in order to obtain survival analysis and finally prognosis of patients. So I am working on something slightly different. I am also informing with tractography maps, but I'm performing principal component analysis on them, kernel principal component analysis, specifically for the time being cosine one. and non-negative matrix factorization combined with clinical features to obtain tract-informed feature set, enriched one. As we can see on the picture, here is an example of obtaining the clinical data together combined with the tractography maps data from principal component analysis. Here I have posted a couple of pictures showing what the principal component analysis output was like. The first two components that I'm showing are very interpretable. The first one shows left and right hemisphere, and the second one shows front and back of the human brain. So this one is interpretable. And I also have some visuals from non-negative matrix factorization, which seems to be doing like brain segmentation type of operations. So my work pipeline is then to work with this tract-informed feature set, perform feature engineering on it, and try with different survival prediction models, such as from different libraries, Python libraries, Lifelines and Psychic Survival. And the survival prediction models I have already used are Cox-PH Fitter, Cox-PH survival analysis, which is the regression, the Cox regression with only rich regression, the CoxNet survival analysis with elastic net regression, and random survival forests. And this yields survival analysis and prognosis results. For the feature engineering, for now, it is only min-max scaling and missing values imported with different strategies, currently median. So this one is to be worked with. And here I have results of different models. They are the maximum results obtained from hyperparameter search, because each of these models has these hyperparameters to put rich regression onto elastic net. And what do the results yield? They show that it is possible to obtain with those cosine kernel, PCA, and NMF components results that are better than just post-operative clinical plus LTDI. However, the numbers are very small and the differences are also quite small. However, this says that there is some information that we can work with. And a natural question arises, like what number of components is optimal, how to find it. And I am now following a pipeline to discover that. For each component, I compute a simple univariate Cox model with a penalty and compute its concordance index. Concordance index is like the area under curve of the survival plot. I calculate the, let's say, predictive power, which is the distance from the index from random guessing, 0.5. And I treat it as components predictive power. I sort the components by the predictive power and compute a Cox model for bigger and bigger feature subsets and pick the optimal one. So this is to be followed. Thank you for your attention.
Many thanks. I understand that also in your case, Joan is a person, let's say, a kind of supervisor, yes? So, and you told that, well, but maybe Joan has something to add. What is really new?
Sorry?
What is really new?
Can you think? What you mean?
What is innovation here in this research?
So yeah, like maybe you can agree that they are competing against each other, no? It's another way of exploring the same concept, I would say. One uses AI, the other one is based on classical machine learning. I think that both of them have advantages and disadvantages. And there's a third person in the lab doing the same with a different method.
So I understand that this is, you have decided to propose Barbara, to use some statistical methods, yes?
So I think that both of them are definitely learning some statistics that are extracurricular for sure. And so there's obviously the learning component to it. And I think that every framework offers advantages, as I said. One is more interpretable and faster, which is this one. The other one is potentially more powerful, but it's definitely slower to develop. So in that, with these two perspectives, we explore the same problem from slightly different starting points. But of course, one of them will be better than the other, and this is difficult to predict. But both of them are show promise, I would say. Yeah.
Well, I understand that you also would like to somehow to put these two approaches together and to make a kind of comparison, yeah?
So it is a possibility, yeah. So for us, we are very interested also in the interpretability, but not in the AI domain, or so from really applying typical clinical workflows or procedures that clinicians understand very easily. So all of this is the backbone, but in the end, so what we are working now with Basha, which he didn't show, is to actually analyze the outcome in the same way that the clinicians do, right? Because for them, that's very easy to understand, while all of these, it's behind the computer screen, let's say. So if you take this into account, maybe the framework that Basha is working on is a bit more interesting or easier to work with, while what Julia was saying, this requires a bit more thinking. But yeah, so essentially they explore the same problem, but from different entry points. And yeah, who knows if one is actually better than the other, or both work, or none of them work, right?
Right. Okay. So, Bashut, any comment on what?
No, perfectly said. Thank you.
Well, any questions from the audience?
At least not at the moment from the internet.
And also from online colleagues? No. Okay, but everything is recorded, so maybe most active persons at this seminar will see it later and come to you with the questions, I hope. Okay, so many thanks, and now we will move to next talk, which will be unfortunately the last one today. Okay, so we have as well as speaker Anna Węgrzyn. Aniu, please go on. Screen is yours, floor is yours.
Thank you. My name is Anna Węgrzyn. I am taking part of Sano Women in STEM Scholarship.
You need to speak a bit louder.
Oh, sorry. So I'm taking part of Sano Women in STEM Scholarship, and my supervisor is Tomasz Kubała. I'll tell you a little about myself. I'm enrolled in biomedical engineering course at AGH University of Krakow. I started these studies because I was always passionate about biology, the human body and processes behind it. However, I didn't want to go into pure biology or medicine because I want to construct something on my own to work exactly how I intended to do. So I tried engineering and fell in love with that. So it became my main interest. I'm currently working on my bachelor's thesis as I am a third-year student. It's focused on the design of photometric sensor for hemoglobin concentration analysis. And I plan to defend my thesis next year. And later, I'm planning to stay in biomedical engineering, but take a little more specialized way and learn more about electronics. So I'm planning to go for master's degrees in electronics and telecommunications, also at AGH University. My main interest in science are electronic sensors that are used in medicine. The way you can acquire the data, the way you can extract the information by signal processing, and every component used in the between final what you get in final. So microcontrollers are my main area of interest. I have to do a lot with them in university and also now in Sano. At Sano, I am taking part in a project designing a coronarography simulator for training future interventional cardiologists. Coronarography is a procedure where the cardiologist inserts catheter into the human body by radial or femoral artery and guides it all the way into the coronary arteries. Where the tip is already there, the main goal is to inject the substance that will visualize the coronary arteries by enhancing its contrast on the X-ray images. And the motion of catheter is depending only of twisting and pushing it by cardiologist at the other end of catheter. So it's a really hard procedure. It requires a lot of practice, and our simulators allows them to practice not only on real patients, but on simulation first. And it tracks the motion behind the catheter, so it can show in computer simulation how it would look in real life. You can see the part of our simulations where the contrast has been already injected into the coronary arteries. And on the right, you can see the hardware part. You can see more about it at previous seminar. And my personal goals to contribute to the project is to design a contrast injection syringe with proper hardware components where the feeling of it in users' hands will be as authentic as possible. And also program it so it can measure the pressure inside the syringe based on what will happen to it. And what I've been already doing in the project is transferring anatomies from real-life tomography scans into computer simulations. It's vascular anatomy on how it should look like in simulation. So a little bit of physics and a little bit of user interface. And beside that, I also take part in other projects, not only at Sano. And one of my latest challenges is taking part in dual tech competition at AGH University of Krakow, where I am designing with my group a rover and a flying drone. It's a great opportunity to learn how electronics components work in bigger systems. I also conducted a workshop on microcontrollers where I could tell more about it to younger students at my research group. And I also participate how I can in various biomedical conferences, as it is always a good opportunity for me to know a little more in the field of new technologies in medicine. And in the spare time, besides of scientific interests, my hobbies are sailing. You can see the picture of me at the coast of Norway. The big part of my life is also contemporary dancing, where you can also see the picture of my latest performances. And as a rest, I also enjoy a good board game. Okay, that's all for me. Thank you for your attention.
So which of these hobbies help in the best way in research?
Oh, I think my dance instructor always told me I have a good feeling of physics, so I think it's something.
Well, sailing also should
Oh
be.
yeah, it's pure physics, I would say.
There is a lot of science in many things. I cannot see Tomek.
Tomek is not here. he apologized already, but he is on the
I think that, as I understand, you need to somehow to transfer the knowledge about human body into the simulator. Yes.
Yes. It's. I think it covers a lot of topics from hardware, from programming, both software and hardware. So everything comes in handy.
Yes, I think that also programming is a challenge because it should be done in real time.
Yeah. It's true. The simulation shows the real time of procedures. So.
And what type of programming language is used for such a purpose?
C# mostly. But yeah, I can tell a lot because it's still under development for commercial purposes.
As I understand, you have started this internship?
Yeah, about a month ago. I'm very new here.
So, it usually 1 month it takes for just to make a kind of recognition what is important, what could be interesting. So
yeah, I'm focusing on that.
Okay. I hope that it will be really a mixture of different things like programming, like sensors. And also the fact that it will be real time, probably it will be a challenge.
Yeah.
Okay. So, if there are no questions or comments, so many thanks for all of them. And also I would like to thank Gosia, who is taking care about, let's say, the way in which what you can feel here in a reasonable way. So thank you.
Thank you.
Well, so this is the end of our seminar. In a week from now, we'll have a presentation of posters which were presented at this conference on high performance computers of Cyfronet. So that's all. Thank you.
Thank you.
Thank you.